So our final lesson in Unit 13-14 here, we get to the first derivative test. So by the end of this lesson, you should be able to use the first derivative of a function to find not only the intervals of increase and decrease, but also the local maxima and local minima of the function. And we'll start by just reminding ourselves of what a critical number of a function is. We said in the last lesson that our local maxima or local minima could occur at the critical numbers of a function. So a critical number is, again, a point on our function where our derivative is either equal to 0 or our derivative does not exist. Okay? For the polynomial functions that we're looking at today, our derivatives always exist, but we're going to encounter functions later on where the derivatives do not exist. So let's say we have found the critical numbers of our function by taking our derivative, setting it equal to 0, and solving for x. What is the first derivative test? Well, it tells us that if we have a critical number of our function, we'll call this critical number c, if at this point c, there are three possibilities. Okay? Our first possibility is at this point c, our derivative, f prime at x, can change sign. It can change sign from negative to positive. So if at this critical point, the derivative changes, the sign of the derivative changes from negative to positive, then this point, c f at c, okay, is a local minimum. And this makes sense because if we imagine a local minimum, kind of like this, we know that if on one side of our local minimum here, our derivative is negative, on the other side it's positive, we must have a local minimum. We'll just label this point C. So that's one possibility. Our derivative changes from negative to positive. Another possibility is that our derivative changes from positive to negative. Well, if it changes from positive to negative, then the first derivative test tells us that this point is a local maximum. And again, if we imagine a local maximum point here at C, on one side of C, our slope of our tangent is going to have a positive slope. On the other side, it's going to have a negative slope. So two possibilities, changes from negative to positive, changes from positive to negative. The third possibility is, what if our derivative does not change sign? So if our derivative does not change sign at C, then this point, C, f at C, is not a local max or min. And what it could be, but it doesn't have to be, but it could be, is something like what we saw in the last example of the last lesson, where our function did something like this at that critical point. This is called a point of inflection. And we're going to look at points of inflection when we get to the next unit. But this is a point where if you look right at point C, you can imagine drawing a tangent there that is horizontal, but on one side of C, slope of the tangent is negative. On the other side, the slope of the tangent is negative as well. So because the tangent doesn't change sign at C, this is not a local maximum or local minimum. Okay. So that's the first derivative test. What do you need to be able to do? You need to be able to answer a question like this. Find the local and the absolute maxima and minima of some function, 4x to the fifth minus 5x to the power fourth minus 40x cubed, on some specific interval, in this case, negative 1 to 5. So what are we going to do first here? Step one is always going to be find our critical numbers. Critical numbers occur where our derivative is equal to 0. So let's take our derivative. Bring down the 5, we get 20x to the 4 minus 20x to the 3 minus 120x squared. Let's fix that 3 up a little bit. Set this equal to 0, and now we want to factor. So we can factor out the 20, leaving us with x to the power 4 minus x cubed minus 6x squared. Sorry? We can factor out the x squared, absolutely. Why do we factor out x squared? The lowest power of x that we see. X squared minus x minus 6. And then we hope that that trinomial is going to factor. Lo and behold, it does. We are going to get x, 3, 2. The 3 has got to be negative and the 2 has to be positive. So what are our critical numbers here? X equals 0, x equals 3, and x equals negative 2. Okay? So these are good places to be looking for our local maxima or minima or our absolute maxima or minima. Now, if you're paying close attention, you might have noticed something about that point x equals negative 2. It is not in the domain of our function, because our domain is negative 1 to 5. So we can basically ignore this point from here on in. Okay? Not in the domain. So now we've got two possible places to look for our local maxima or minima. And then when we get to the end, we're going to bring in, also going to take a look at our endpoints to see which is our absolute maxima or minima. So how do we figure out whether these things are maxima or local max or local min? Well, we want to check the sign of the first derivative on either side of the critical numbers. How do we check the sign of that first derivative? We're going to set up an interval table here. So we're using 0 and 3 to define the ends of our intervals, and the other numbers we're going to use are our endpoints here. So our function has an interval from our one endpoint, -1 to 0, from 0 to 3, and then from 3 to our other endpoint, which is 5. And that's all we're interested in, because that's the domain of our function. And again, we want to check the sign of each one of these terms in our first derivative. So we've got 20x squared, x plus 2, and x minus 3. We're checking for the sign of our derivative and also for what it tells us about our original function. So 20x squared is going to be positive no matter what we do. X plus 2 is going to be positive, positive, and positive. Let's see, -0.5 plus 2, yep, positive, positive, positive. And x minus 3 is going to be negative, negative, and positive. So our derivative is negative, negative, and positive, which means our function is decreasing, decreasing, and then increasing. So we were asked first to find the local max and min. Do we have any local maxima or local minima? Right. Yeah. So right here at x equals 3, we have a local minimum. How do we know this is a local minimum? Because the sign of the derivative is changing from negative to positive. Our function is changing from decreasing to increasing. So local minimum at x equals 3. If we sub 3 into our function, we get negative 513. It's a pretty big local minimum. So we have one local minimum of negative 513 at x equals 3. If we want to find our absolute maximum or minimum, we need to check our endpoints as well. Because those absolute max and min can occur either at the critical numbers or at the endpoints. So we want to find f at -1 and f at 5. Punching this into our calculator tells us that f at -1 is 31, f at 5 is 4,375. So, what is our absolute maximum here? Well, largest possible y value, considering our critical point and, our local minimum, our two endpoints, tells us that our absolute maximum is 4,375 at x equals 5. And our absolute minimum is going to be at our local minimum. Negative 513 at x equals 3. So there we have it, our one local minimum on our domain, and our absolute maximum and our absolute minimum.